All right, thank you. So this is the vision section, and I would like to make it a little bit more general and talk a little bit about the problems of perception in the cyber-physical system. So my area of interest is the computer vision and robotics, and I sort of try to straddle the boundaries between the two. And so I'm interested in computer vision. In particular, I'm interested in coming up with techniques and algorithms for perceiving the real world such that the representations which we attain can be useful for robotic tasks. So there is always this sort of vision component with a particular robotic tasks in mind, which of course brings its own specific set of problems. And I'm interested in designing systems with enhanced autonomy and building more and more complex models of the environment so more sophisticated tasks can be accomplished by robotic systems. So I decided to give you a little bit of a journey through my career, going from my starting work during my PhD on discrete event systems and hybrid systems all the way to deep learning, because I was sort of fortunate to be exposed to all these techniques and models in sort of fairly limited class of problems. And that I think sort of gave me a good understanding what are the trade-offs between using these model-based techniques and these data-driven techniques, and also what are the open questions going forward. And so given the fact that a large portion of the audience here is sort of interested in hybrid systems and asking sort of questions and properties, being able to prove certain properties about the systems, I'm going to discuss techniques where we have been very successful in doing so, and then I'll try to contrast it a little bit with more these data-driven and empirical methods, and I'll try to sort of find that common denominator by talking about the parameters this model have, because those are effectively the type of things which can vary, or we can sort of try to understand or gain some introspection capabilities into. And I'm going to do it in the context of tasks of vision-based control for driving and for robotic manipulations, multi-agent control, and then sort of the general autonomous driving as it is sort of currently popularized, I guess on popular press and also by various research groups. So I have started working on these problems already during my PhD thesis, and this is going to be a little bit out of order, but I'm going to start with the work which we have done here in 1996 with the Autonomous Highway Project with Praveen, Shankar, and Jitendra. We were tasked with the goal of trying to design a vision-based controller for cars for staying in the lanes and doing lane change maneuvers, keeping the distance from the cars ahead. And so these were the sort of the basic vision control modules of the intelligent highway systems. And we were very successful. We have gotten the cars from Honda. We sort of built a prototype of the system within the year and tested it and managed to drive in 70 miles an hour in very clean environments. And on the top of it, we were able to prove very nice properties of the system because we had nice models of the car dynamics. And we have nice observers, and the vision or the perception component of the entire system was limited by simply sensing two state variables, and that was the offset at the look ahead from the lanes and the angle at the look ahead. So this was a fairly clean vision problem, and extracting this information from images maybe required tuning on the order of 10 parameters, which were some thresholds in order to make the system robust, but the number was fairly small that we could sort of empirically test it in order to sort of be able to provide at least some empirical guarantees that these parameters will be estimated reliably. And with a little bit more effort, we could maybe associate some uncertainties or confidences with this estimate. And similar type of methodology has been then applied in the context of this autonomous landing, where again the quantities vision was trying to extract from the environments were very simple. We had some sort of little corner landmarks which we could track reliably. So the conclusion of this stage was that we had very nice models. We could prove nice properties about the models. But the models of the environment or the job of the perceptual system was extremely simple. So we have taken this very rich source of data, which were these video streams, and we basically boiled it down to 2 state variables and maybe in the process developed algorithms where we needed to adjust maybe 10 parameters. And this was all kind of engineering sort of enterprise. You know, we sort of understood how our pixels work. We understood the variations which we can encounter in the environment, and we were sort of successful for the time being. So then, you know, moving sort of forward, I was always sort of interested being able to do perception for more sophisticated tasks and being able to understand more of the environment better. And I had an opportunity to explore that in the context of slightly different tasks, and this was the sort of the multi-agent coordination and control task, where in addition to needing to accomplish certain goals, where the goals for the robotic agents were just simple navigation goals, reaching the goals, we had to also be able to guarantee some coordination between the vehicles. And here, the model of the environment where the perception was trying to extract was simply just free or occupied space. And again, at that time, there was a very good methodology for tying what the perception was extracted to some sort of functional models which could be sort of nicely plugged into the control properties. And in those settings, the models were represented using so-called navigation functions. And again, given the navigation functions, one could nicely guarantee that these controllers will indeed reach the goal if the sort of the conditions are satisfied. And this also enabled us to look at some more sophisticated tasks and look at some compositionality properties. So the modularity and compositionality sort of became apparent, and this was sort of around the time which gave rise to the hybrid system, where we started seeing the models where the finite state machines were sort of modeling the compositional properties of the behaviors, whether it was the sequential composition or parallel and so forth. And within the states, we had the continuous controllers running. And in this setting, both achieving the goals, so some reachability properties were attainable. And in the context of different tasks, people look at some safety properties and so forth. But again, in this setting, the environments were still very simple, and the perception modules were quite brittle. So then came a period where people would just put lots of sensors on the vehicles. And this was sort of the period of grand challenges. And here, again, the sophistication of the environment where these autonomous agents could perceive went all the way from sort of this driving through the desert environment to more urban-like environments. But really, the perception component here was really just trying to determine where is the road and where are the obstacles. And in order to do that, the equipment which these vehicles had to carry was sort of quite extraordinary. There were lots of very, very expensive laser rangefinders, compass, IMU, GPS, everything. And you know, there was a lot of publications how to integrate all these techniques together and be able to also, in certain settings, guarantee certain properties. So I think we as a community sort of made some headway in understanding and putting a little bit more emphasis on the compositionality, modularity, reachability, and safety, and also formulated questions and problems about what kind of properties we can then prove or state about systems which have this sort of hybrid nature. And from the perception side, maybe the number of parameters which our algorithms use to extract these models of the environment were maybe on the order of 50. Okay, so we went, say, one magnitude more than what we had when we were just doing simple driving. And again, we could do it because we had a lot of intuition how things could be done. But still, the type of things which we could extract from the environments were extremely simple. It was basically maybe just the other cars and the free space. So in the meantime, in the parallel universe in the computer vision community, there was sort of an increased sort of desire to get more and more deeper understanding from images, and this, of course, sort of propagated to the area of autonomous driving. And so one of those sort of holy grail problems which people worked for a number of years was the problem of simultaneous segmentation and labeling of the video stream of the data, such that you can sort of take the video of the street scenes and out comes the representation which you see on the right, where you can basically provide a pixel level labeling of the semantic categories you encounter on the street, right? So you can say, hey, this is a sidewalk, there is a road, column poles, building, trees, and so forth. And so, and let's say the number of semantic categories was on the order of 10, 20, 30. And we can argue which of these categories are required for driving tasks, but you can imagine situations that this is extremely useful data for lots of purposes. And if we focus only on driving, knowing where cars and pedestrians are, roads and obstacles is extremely important, because those are the things we may want to reason about the properties of these objects, because cars can move and pedestrians can move and so forth. Okay? So this is, the community spent maybe 10 years developing models to solve these problems. And that effort proceeded roughly in the following way. So one had to make a model choice. And that model choice typically required some sort of inference problem on the graph where some features needed to be chosen. And again, in computer vision, we were extremely good in designing features. This is what the community sort of spent a lot of time sort of engineering features in order to sort of be able to guarantee some of these invariance properties, and then sort of putting things together and modeling spatial relationships features, and then the process of tuning the parameters by hand, which we used to do before, ended up being formulated as a problem of learning the parameters, because this was the inception of the data-driven age, where we had a lot of examples how things should be labeled and learned. So instead of just fine-tuning things by hand, we can actually design optimization procedures which would optimize the optimal set of parameters given the data. And so this was typically handled in these conditional random field frameworks or Markov random field frameworks, depending on the setup, which were kind of modeling the spatial interactions between the sites in the images, and were sort of characterized, or these models were parameterized by these simple classes of functions where the parameters could be learned. And even in that setting, this is an extremely rich area where a large number of works has been done in the optimization setting. And so there is sort of reasonably good understanding when global properties of these models can be guaranteed. But even if we can guarantee the global convergence properties, the choice of the model was still questionable, right? Because there were all these features and parameters which we have decided prior putting things into the model. But nevertheless, we have made some headway. So we could reconstruct the environment, and we could label pixel level labeling, and this worked fairly well in both indoors and outdoors environments. I am not going to give you the numbers, but I'll be happy to discuss that. So this is some examples from the street scenes, and then we had some examples from the indoor settings. And the performance, depending on the complexity of some of these number of semantic categories, was in sort of 80% performance. And here, the number of parameters which we had to learn was fairly small. It was in the order of 50. But then the additional benefit was that we actually could learn these parameters. So there was this feeling that we have this principled way how we can determine it. And then we would use either cross-validation or these learning methods to come up with these parameters. However, what was still hand-designed were the features, right? So this was the choice of the model was really in the hands of the designer. And so there have been a lot of efforts trying to sort of figure out what are the best choices. And there was some sort of fairly finite number of possibilities, but within each of these possibilities, a lot of choices of the parameters had to be made, and that's not really accounted in that 50, okay? And so then, so we have spent a number of years exploring these avenues, and then this sort of data-driven deep revolution came about, where the idea was basically saying, why don't we just learn everything from data? So with the inception of these convolutional neural networks and these deep learning architectures, it suddenly became possible to give it an input and image, and given an output, either the semantic segmentation or 3D reconstruction or categorization, and basically learn the entire mapping. And one reason why it was possible, because the architecture itself kind of resembled, to some extent, a lot of the feature extraction and processing, which the computer vision researchers have been doing, and René sort of gave also a little bit sort of brief overview of that. But what was appealing about it, that there was basically this monolithic architecture where everything could be optimized jointly and could be thought of as just this large number of weights, which would then be viewed as these convolutional filters, which could be shared without layers, and these nonlinearities, which were viewed as sort of mechanisms for integrating this spatial information between the neighboring regions. And so this happened, so we decided, well, we have to try it. You know, everybody is talking about it. So we did, and it worked remarkably well. So let me tell you what the model is, and then I'm just going to have a lot of questions, and I hope you'll help me answer some of them. So we basically have designed a model of this convolutional neural network, where the starting point of the model is the famous ImageNet model, which René mentioned, which was sort of the first model of this convolutional neural network, which was trained on this categorization problem. And this is the model. We ended up using the best performing model, and that had 136 million parameters. And this is the so-called VGG network. I want to mention also that, you know, one wonderful effort of the community is that if somebody trains the model, they make the model available. So that process of starting from the random parameters is no longer a starting point for everybody, because you can actually start with a model which was pre-trained by somebody on a slightly different task. And furthermore, you can study how your new task really affects the choices of the parameters of the initial model, because then you can fine-tune everything together. So we've started with this 160 million parameter model, which was trained on recognition. And the beauty of that model is that that model has seen a lot of images. It's seen 10,000 categories, 1.2 million images, and that model already learned some basic invariances which were present in the data set. And there is some sort of understanding, which is of course only sort of intuitive, and via some introspection of the network, is that the model in fact does learn some of the invariances, which previously we were striving so hard to design features in order to be able to be invariant with respect to some of these transformations. This is lighting invariance, a little bit of viewpoint invariance, translational invariance, and so forth. And then on the top of it, we build our task-specific part of the network, where we simultaneously can then do the semantic segmentation and also 3D reconstruction. So this is now the problem which we are trying to solve is, given an image, we would like to both attain a pixel-level labeling of what are the semantic categories in the image, but we also are able to attain what is the 3D model of that image. And this can be done again with unprecedented accuracy, given this model, which has this huge number of parameters. And so there are a lot of things which one needs to do in order to make it work. So there is this issue of how to design the loss functions. There is an issue of how to train the model. There is an issue how to connect it with a more structured type of models, which have been used in the past. And I don't want to go through the technical details, but on the top of the convolutional model, we actually have a conditional random field model where we can jointly train the parameters of the model with the network, and ended up getting sort of unprecedented accuracy. So let me sort of tell you a little bit about the training, and I want to just mention it because this is the place which sort of can give you a little bit of insight that despite of the fact that at first sight these models are these extremely monolithic models and they seem to be trained this end-to-end for the task, they're in fact pieces of them are these reusable components which can be actually trained independently and then just fine-tuned with the remaining components. Okay? So we would have the first model which we trained initially was just the model for the semantic segmentation. So we'll have the weights, and then we add, and we initialized all the models using the grade model which has been used for the recognition challenge. And just to sort of clarify, the recognition is that given an image, you just want the one label. What is in the image? Car. Here the model is, given an image, you want to pixel-pixel mapping between what are the labels of individual pixels. So there are a lot of subtleties how to do this in the multi-resolutional settings, because if you do the pooling, the resolution is reduced, then you have to extrapolate. But, you know, so the field is moving extremely fast. We have sort of figured out how to do it. Then we added a depth model. And again, we can train the depth independently. And what's remarkable that the features what the depth model is using are in fact shared with the semantic segmentation model and are only fine-tuned slightly in order to optimize again for the training set, in order to get the 3D reconstruction. So two very different tasks, but the low-level core is shared. And on the top of it, we'll add the fully connected conditional random field model where the interactions between the 3D depth reconstruction and the semantic segmentation sort of where they interact. And this all can be trained jointly using backpropagation, and these are some of the results. So here are, you can see now the complexity of the environment. It's unprecedented compared to what we were able to perceive using our hand engineer feature method. So we have an image on the right-hand side, and this is sort of a little bit blurry. The visualization is not great, but this is the depth map, which has been recovered from that single image. And the last column are the color-coded semantic categories. So even if you are just interested in the road, so notice that in all cases, the road has been extracted very reliably, despite difficult shadow issues, different lighting conditions, something which would be very, very difficult to do in the past. The purple blobs are the cars, then you have the buildings, then you have the trees, which are the dark regions, and a few more of these. So this is where we are. I also want to mention that this is sort of dramatically changing the pace how the research is done, because, you know, it's sort of remarkable. I was just talking to the students, to some of my colleagues, how the meetings with the students look like at the moment. So before, there was a marker and the blackboard, and we would be brainstorming, and now it's more like, so how is it going? Well, it's still training, so, you know, I need a better GPU. And so it's, I personally feel that, you know, one needs to really kind of pause a little bit, because when one thinks about educating the generation of new students who are so extremely skilled in using these tools that, you know, I have given the student this idea just a week ago, and within a week he came up with these results, which is something 2 years ago you would have taken a couple years for a student to deliver anything even reasonably close. You know, I think brings a lot of open questions, even how we should sort of educate and what the curricula should be in this sort of data-driven age. So going forward, I think we have still a lot of interesting questions and challenging ahead. I think the modularity, compositionality, safety, and learning in the age of these data-driven methods are still super interesting problems. And I all encourage you to think about it, because although they seem to be daunting, they are sort of there and they're appearing there, and they're very much resembling some of the ideas which we were discussing in the age of hybrid systems. But the techniques, the computational methods are different. Whether we should consider these end-to-end learning architectures, or whether we should still consider architectures where we have perception, action, planning, control, things happening at different time scale, that's also another interesting and important question as we move forward. And I cannot not end without, quoting my favorite quote, which I still have in my head from my time in Berkeley with Shankar when we were sitting at Nefeli and working on our geometry book. Shankar always used to say that the day without an equation is a day like a day without the sunshine, which in California, you know what that means. And so I hope we'll have many days like this. Maybe equations will be different, or the kind of things we'll be discussing will be different, but I think this is still a good quote to end with.
Thank you very much. Are there any questions for Jana? Quick ones. That was really a lovely talk. Yes.
So maybe the answer is too long, so we can do it after. I was very, very impressed that you can do end-to-end training with the conditioning learning. I thought it was very, very hard. And the main reason being that the output of the network is structured, because you would like labels in nearby pixels to be related as opposed to the traditional way.
So,
in most of the prior work was just pre-training with the first part and training the CRF separate.
So this is only possible for certain kinds of CRF models. So this is not a completely general statement. So this is possible for these Gaussian fully connected CRFs, which are very regular, right? So they do not have these sort of specific structures, but they're very regular, so they kind of conform nicely to the monolithic style architecture. So yeah, it's not by no means general statement. If you want to have more sophisticated models, you have to train things separately.
I think we have to move on. Thank you very much, Jana.
Thanks.